displacement x, velocity v, acceleration a, and time t are related. Let's derive how each term is related to the other. Before deriving the kinematic equations, we have to learn about a, t, and vt graphs. You know that acceleration can change with time and the position of the body. Here, we will deal with bodies moving with constant acceleration. VT graphs help us understand the given problems a little more clearly and solve them easily. Let us look at one interesting aspect of the VT graph. This graph actually helps find the displacement of a body. Let us consider an example where a body is moving with a constant velocity, v, during the time interval, t, where t is equal to t0 is equal to 0 to t is equal to t1. Let us draw the VT graph representing this motion of the body. We get a line parallel to the x-axis. We know that velocity of a body is the ratio of its displacement and the time interval. We can say that displacement is a product of velocity and the time interval. This is the product of velocity v and time interval t1. This is nothing but the product of the height and the length of the rectangle formed when a line is dropped perpendicular to the x-axis. That is, the area of the rectangle. The area under the line up to the x-axis indicates the displacement of the body. The same concept applies to bodies moving with a constant acceleration. In this case, the VT graph will be an inclined line, and the area under this inclined line up to the x-axis represents the displacement. There are three important kinematic equations for uniformly accelerated motion. Let us derive these equations one at a time. The first equation is the relation between initial velocity v0, final velocity v, uniform acceleration a, and time t. The velocity of an object is v0 at t0 is equal to 0 and v at time t. Average acceleration a dash is the ratio of the difference between v and v0 and the difference between t and 0. The value of a dash is equal to acceleration when acceleration is constant. By cross-multiplying and rearranging, we get the value of velocity as the sum of v0 and the product of a and t. This is equation 1 of motion. The second equation represents the relation between displacement x, initial velocity v0, acceleration a, and time t. The area under the line PQ up to the x-axis represents displacement x. Displacement x is represented by the area between the lines joining points O, P, Q, and S. This is equal to the sum of the areas formed by the triangle PQR and the rectangle PRSO. We get the value of x as half the product of t, and the difference of v and v0 plus the product of v0 and t. From equation 1, the value of v is the sum of v0 and the product of a and t. Here, the value of the product of a and t can be derived as the difference between v and v0. Now, replacing the v minus v0 in the equation by at, we get x is equal to v0 into t plus half at square. This is equation 2 of motion. The third equation is the relation between initial velocity v0, final velocity v, acceleration a, and displacement x. The average velocity of a body v dash is half the sum of v and v0, where acceleration is constant. We know that displacement is the product of average velocity and time, that is, the product of v dash and t. From equation 1, v is the sum of v0 and at. By rearranging the equation, we get time t equal to the ratio of the difference of v and v0 and a. Substituting the values of t and v dash in the equation for displacement, we get x equal to the ratio of the difference between v square and v0 square, and twice the value of a. By rearranging the above equation, v square is equal to v0 square plus 2ax. This is equation 3 of motion. Let's now use calculus to derive the equations of motion that were derived so far using basic mathematics. The new set of equations we shall derive is very useful in solving complicated problems. Let's start with uniform rectilinear motion. Observe the xt graph. t0 is not equal to 0 and x0 is also not equal to 0. dx by dt is equal to v, which is a constant. Initial values are x0, t0. Final values are x, t. Cross-multiplying equation 1, we get dx is equal to v into dt. Integrating both sides, we get integral x0 to x dx equal to v into integral t0 to t dt. We get x minus x0 is equal to v into t minus t0. On transposing, we get x equal to x0 plus v into t minus t0. This equation is used to obtain the position coordinate x of the body at any time t. This equation can be used when the values of x0 and t0 are both or either of them is equal to 0. In other words, the equation is applicable under all conditions. Now let's derive equations for uniformly accelerated rectilinear motion. In this type of motion, the acceleration of the particle is a constant dv by dt is equal to a, which is a constant. The initial values are x0, t0 and v0. Similarly, the final values are x, t and v. dv by dt is equal to a. By cross-multiplying, we get dv equal to a into dt. Integrating both sides, integral v0 to v dv is equal to a into integral t0 to t dt. v minus v0 is equal to a into t minus t0. Rearranging the equation, v equals to v0 plus a into t minus t0. This is equation 1 of motion. We know that dx by dt is equal to v. Substituting this value in equation 1, we get dx by dt is equal to v0 plus a into t minus t naught. By cross multiplying, we get dx is equal to v naught plus a into t minus t naught multiplied by dt. Integrating both sides, we get x minus x naught equal to v naught into t minus t naught plus half a into t minus t naught whole square. This is equation 2 of motion. v is equal to dx by dt and a is equal to dv by dt. From equation 1, dt is equal to dx by v. Substituting the value of dt in equation 2, we get a equal to v into dv by dx. We know that this value of a is a constant. By cross multiplying, we get v into dv is equal to a into dx. Integrating both sides, we get integral v naught to v. v into dv is equal to a into integral x naught to x dx. This is equal to half v square minus v naught square equals to a into x minus x naught. Rearranging the equation, v square is equal to v naught square plus 2 a into x minus x naught. This is equation 3 of motion.